So we are still in this world of solutions, and in particular today, I'm going to be talking about wind energy and solar energy and storage of energy, so like battery storage of energy. And we're using En-ROADS. So first I want to review why we're really talking about, why we're going to be emphasizing renewable energy. And so I want to do that by going back to our Kaya identity. But so if you go to En-ROADS, you're at the default screen. Under View, there's Kaya graphs. And so anything that you play with the levers, you'll see changes in the Kaya graphs. And so that will help you understand where your emissions reductions are coming from. So just to remind you about these graphs relative to the way that I showed it before, we have basically our four terms in these graphs. So we have our number of people on the planet, number of people on the planet increasing from about 6 billion people in the year 2000 up to about 11 billion people by 2100. So our CO2 emissions are going to be related first to the number of people on the planet. Then we're going to multiply that times the GDP per capita. And then these also have this time dimension in here too. So it's like GDP per capita, which is measured in dollars per person per year. And so people are going up, GDP per capita is expected to go up by a lot. So multiplied by almost like 6 times by the year 2100. So we're currently not in a situation where GDP per capita is going up, right? We're in an economic crash, but these still predictions for a long-term trend by 2100 would be that we would still grow quite a bit by 2100. So goods and services consumed per person, especially in the developing world, especially in India and China, and later in the century, Africa, are expected to increase by a lot. So the standard of living is expected to increase a lot globally over the next century. So more people consuming more things. And then we have our kind of energy efficiency. So it's called energy intensity of GDP. So that's the energy required to produce a given amount of goods and services. And that is expected to decrease. So that's good. So we are getting gains in energy efficiency. And then we multiply that. So all these three things multiplied together would be our total energy use. So population times GDP per capita times how much energy is used per GDP is going to be total energy use. And then to get how much CO2 emissions we are going to produce from that, we would multiply that by our rate of CO2 emissions per unit of energy. And so we see that is also expected to come down, but not very fast, right? So it's kind of slightly coming down. So we have 2 that are going in the right direction for reducing CO2 emissions and 2 that are going in the wrong direction for reducing CO2 emissions. But we don't want to really mess with these, right? Like we don't want to put population controls on the population globally, and we don't want to inhibit economic growth, especially in the developing world. So our main levers for reducing CO2 emissions are going to be in this reduction of the energy intensity of the economy and reduction in the carbon emitted per unit of energy. And so you multiply all those together, you get CO2 emissions. So in the baseline scenario for En-ROADS, we have CO2 emissions increasing by quite a bit, still by 2100. And that is going to be related to global temperature. So we want to think about how best to reduce emissions. And in order to do that, really our best bet, so I'll give you a link to this scenario, but whenever we come up with some scenario in En-ROADS where we're doing a bunch of levers and we're getting to temperature stabilizing at somewhere around 2 degrees Celsius, what you're going to see is you're going to see mostly this coming from a reduction in the carbon intensity of energy. So here's an example, and there'll be a link here that you can click on. And so in this case, I'm stabilizing global temperatures below 2 degrees Celsius over here. And I'm not doing it by changing the amount of people on the planet. I'm letting that grow to 11 billion. I'm not doing it by changing GDP per capita. I'm letting the economy grow the way that it would have otherwise. I am getting help by increasing energy efficiency, getting more out of more goods and services per unit of energy. So that's decreasing faster in my scenario here. But the big gain comes from zeroing out these emissions of CO2. You notice these CO2 molecules are gone here. So if you can get your energy from sources that are not emitting CO2, that solves your problem, right? So this is showing this major reduction in the amount of carbon produced per unit of energy. And so then your CO2 emissions get down to zero. The emissions again are the faucet. So you need to get emissions down to zero to get your bathtub to stop rising. And so when your emissions are down to zero, then your temperature stops rising and stabilizes at about 2 degrees. So how do we actually do that? My global sources of primary energy. The way that I got these to stabilize was I taxed my fossil fuels, coal, oil, natural gas. I put on a high carbon price. I increased energy efficiency for both transport and buildings and industry. I also electrified those, meaning that I'm getting my energy from electricity rather than, for example, burning oil inside the car. And so what happens is, in this case, like by 2060, most of the energy is coming from renewable energy. So renewable is our green line here. And so renewables include a whole assortment of things like geothermal and tidal energy and hydropower, but mostly we're talking about solar panels and wind turbines, so wind and solar energy. But there is kind of a catch here. So we've reduced our CO2 emissions by switching over to renewable energy in this scenario. And this is what our energy mix looks like by 2050, 2060. We have a situation where most of the energy is from renewable energy. But there are major costs to this. So here's our graph of the dollars per gigajoule, so the amount of money per unit of energy. And so we've gone from something like 25 to over 60. So we more than doubled the cost of energy by essentially taxing all of the oil, coal, natural gas, and putting a carbon price on all emissions. And so what that's doing is it's making renewable energy more attractive financially, because now all these other sources of energy are more expensive. So we do have this major increase in the cost of energy. And I will just show you in here how to get to that. So you click on this drop-down menu, and you go to financial, and you go to cost of energy, and that's where you can see that. So we have this big cost of energy that then eventually starts coming down. But I kind of want to just talk about like where that comes from, so that you have an understanding of why this is a challenge and why it's been hard to get countries to actually sign on to their climate goals, why it's difficult to get China and India and the United States and Europe and Australia and Brazil and everyone on board to actually switch over to renewable energies. And it's basically, because of these costs. And so let's talk more about like where these costs come from. So there's another thing that we can look at, the marginal cost of renewables. And so this shows us costs. This is dollars per megawatt hour, so dollars per unit of energy. And they have it split into the cost of renewables themselves and then storage costs. So that's interesting. That's kind of giving us a clue, like, okay, so it probably costs something to, actually build all of these wind and solar farms. So that would be this purple area here. And then storage costs also comes on there. So that's telling us that we need this additional spending. We need to take resources away from other areas of the economy to create storage of energy. So to create batteries. Another way that we could store energy is potentially, it's called pumped hydro, where you just kind of pump water like up a hill and then you can release it later. And that can spin a turbine and generate electricity that way. So that's another way to store energy. But that's telling us that, okay, there's multiple costs, including the cost of storing energy. And so that kind of brings up an interesting aspect of this that we'll talk about today. So the costs essentially are coming from that we have to build new things for this new system. So we have to build the literal wind and solar farms. We have to build kind of a new electrical grid that I'll show you why we have to do that. And then we need to store a bunch of energy, and I'll show you why we need to do that as well. And it turns out that storage is a major barrier for renewable energy. So it costs a lot of money to store energy, and we didn't really need to do this before. And so this is why this is a challenge economically. And then since it's a challenge economically, it's a challenge politically. I will show you that in En-ROADS, you can kind of manipulate a little bit like how optimistic or pessimistic we might want to be about the future costs of renewable energy. So here's our plot from before of the cost of energy kind of in the default assumptions, cost of energy under high renewable scenario without a technological breakthrough. But there are levers in here that you can manipulate to kind of be more optimistic about a technological breakthrough. So there's this drop down under renewables. Yeah, so if I just click on renewable ... and then go down here to renewable R&D breakthrough cost reduction. So that's in percent terms. So you can turn this way up. And so this is the percent that a research and development breakthrough suddenly reduces the supply cost of renewable energy. The values represent a decrease in cost from the point when the breakthrough occurs. So then you can set a year for when the breakthrough occurs too. So this would be later in time, this is earlier in time. So this is saying that, okay, we're gonna have some major breakthrough because maybe the government is sponsoring a program to do research on renewable energy, or I just think that some tech firm in Silicon Valley is gonna come up with something and it's gonna drastically reduce the cost of renewable energy. And so that's gonna help us in terms of the economics of this transition and then the politics of this transition as well. So you can increase that by 50%. And then they also have this storage breakthrough cost. So they have this other component of storing the energy that we can also potentially imagine a breakthrough in that, let's say 100% reduction in the costs associated with storing energy through some breakthrough, either government sponsored program or through private industry that then gets scaled to large portions of the system, of the economy. And so when we do that, we can get a situation in En-ROADS where the cost of energy still spikes initially, because remember we said in this scenario that the breakthrough comes in 2030. So it's not coming today, it's coming 10 years from now. But then once that breakthrough is able to be scaled, I mean, it takes a lot of time to actually build out the infrastructure and to commercialize some type of a new invention. But if you do that, if you combine breakthroughs in both renewable energy and in storage costs in En-ROADS, you can get a situation where eventually you actually have renewables costing less than they would have otherwise. So by the latter half of the century, so by the 2070s, you have this blue line below the business as usual scenario, where you're saving money in terms of the system. The energy system just by itself is saving the world money. It's saving the world production. It's saving the world goods and services. And that's not even taking into account all of the savings from not having climate change. So all the savings that you get from the benefit of reducing CO2 emissions. So that's interesting. But in the baseline scenario, it is the case that renewables remain more expensive than the conventional energy system throughout the remainder of the century. And so then we talked about last time that you would only want to do this from an economic perspective if you saw that the costs of CO2 itself were enough to justify the benefits of this increased cost from switching to renewable energy. And we do think that that is the case, which is why, you know, all this policy is being proposed to reduce CO2 emissions, despite the fact that the renewable energy system may cost more. So let's get into a little bit more of the details of why it costs more.
All of your appliances work. Your power company has electricity ready to transmit for a lot of customers. And utility companies have gotten really good at anticipating that demand.
If the grid managers are doing their job, you should never notice any of this.
But a rise in solar energy production is making their jobs a bit more complex. Here's a chart that explains why. It's showing demand for electricity at any given time of day. The power companies supply the least amount of power overnight. Then it ramps up in the morning. Everyone's woken up and business gets going. Then at sunset, energy demand peaks. Utility companies will update models like this to operate as efficiently as possible. But the introduction of renewable energy, particularly solar energy, has started causing problems in these demand curves. In 2010, solar panel deployment really started taking off. Most of those installations took place in California, so researchers there started looking into it. They found that the sun produces the most energy at midday, and when you factor in that new midday production, your demand curve changes like this. Every year means new solar capacity, which makes midday demand dip lower and lower. Researchers call this drop in demand the duck curve.
From the grid manager's perspective, the people whose job it is to constantly balance generation and demand, it looks like a drop in demand.
That drop in demand creates two problems. The first has to do with the intense ramps in the new chart. As the sun sets, solar energy production ends, just as the demand for energy typically peaks. Power plants then have to rapidly ramp up production to compensate for that, which is kind of hard to do with the current fleet of power infrastructure. The second problem is economic.
Say you have a couple of nuclear and coal plants. Those plants are only economic when they are running all the time, basically. They run around the clock. And if you have to turn them off at midday, it completely screws up their economics. And plus, lots of utilities just have contracts with those power plants to keep them running all the time. So that creates sort of an artificial floor. If solar generates too much power and there's no use for it, there's no one to consume it, then grid managers just have to turn some solar panels off.
If they didn't, we could risk overloading or even damaging the power grid. So we throw away some of that extra solar energy.
Effectively, what's happening is that solar power is being wasted.
That waste, curtailment, is the big challenge moving forward for solar energy.
If you want solar eventually to power everything or close to everything, you've got to figure out some way of shifting some of it to the nighttime, right? Because the sun's down during the nighttime. The more power can be stored, the more you can sort of let solar rip.
While the grid managers figure out how to serve this new supply and demand, this duck is the greatest challenge facing renewable energy.
Okay. So the basic idea here is that um, we're used to this traditional power system that matches our demand for power in real time with supply that it can just kind of turn up or down. But with a renewable energy system, with wind and solar, we're not in charge of when the sun shines the most and when the wind blows the most. And so we have to start adjusting to that or start storing energy a lot in batteries, which we've never done before at utility scale. And so it's interesting in California, we can look at what they're talking about in real time here with this. So I have a link to it in the slides there. But this is California ISO, so they track our energy supply. And so we can see on a minute by minute basis, like where our energy supply is coming from right now. And we can see that phenomena that they're talking about in the video where, when the sun comes out, we have a lot of solar panels. We're now using a lot of that solar energy, or there's a lot of solar energy available, but it's not necessarily the case that the demand increases, the demand for energy increases right at the same time as supply. But it is cool to see, we're close to, so it's 11:07 a.m. Solar noon is around 1 p.m. this time of year here. So we're getting closer to solar noon when the sun is highest in the sky. And we can see that we have renewables in California anyway, are by far the #1 source of electricity. So that's, quite different than global energy supply. Renewables are not a large fraction of global energy supply, especially when we look at these in terms of area. Just a tiny fraction is renewables. But in California, when we're talking about just electricity, so not the energy used for transportation and things like that, and we're talking about just in the middle of the day, then renewables are a large fraction of our electricity supply. So this is what it is right now at this minute. It's 60%, which is mostly solar. So 65% of the renewables is coming from solar and 22% from wind. And then the stuff that's non-renewable is basically natural gas. So in California, we're doing a lot better than a lot of the rest of the world, frankly, in terms of generating electricity from renewable sources. So we'll see a lot of the problems that come from renewables first, but we can be kind of a model for the rest of the world's energy systems as well, hopefully. And so this is to remind you that we have laws on the books that are requiring 60% of our electricity to come from renewables by 2030. So that's total electricity, so not just at the highest, not just in the middle of the day when the sun is the brightest, but 60% overall. And then by 2045, the law requires that all the state's electricity come from carbon-free sources. So we are moving in the direction of more wind and solar. So that's why I wanted to talk about what the main challenges are to that system. So I'm going to do that with a map and a graph of power supply and demand. So let's think about, let's just say, okay, society is here. We are representing society in this demonstration. And so historically, we've powered our societies by burning fossil fuels like coal and natural gas. So we have some power plants that, we dig up fossil fuels somewhere and we transport them by train to the power plant. And then we burn it, and that turns a generator, which then allows electricity to flow to society. And so these, we've found that these fuels do provide reliable energy at apparently pretty low cost, at least in the short run. But, they do have a large cost in the long run, which is why we're eventually trying to get away from them. But one advantage is that the energy is like pre-stored, right? A lump of coal or a barrel of oil or a barrel of natural gas, that energy is not going to disappear if you just leave it sitting there in the yard of the power plant. So it's already stored. We don't need to store the electricity. So it's stored in the chemical bonds of the molecules. And what that means is that you can then burn more when society wants more energy, and you can burn less when society wants less energy. And so if we think about our power demanded, so this would be like just one typical week, our demand for power from society, they kind of just showed it in the video. It has this kind of daily cycle where essentially each evening is when our demand peaks. So like kind of 6, 7 at night when people come home from work, but the offices are still, all the lights are on and things in the offices, and people are back at home and turning on their appliances and running their TVs and their computers. That's when demand peaks kind of every day, the power demanded by society. And so in this previous system, we had what we would call baseload power. So we would have like coal that would meet kind of the minimum amount of power demanded by society. And then we would have additional sources of fossil fuel burning power generation like natural gas that we kind of turn up and down quickly. And that gets called dispatchable supply of energy. But you have this system where basically the supply of power matches the demand of power, and we're kind of in charge of that. We can move supply to match demand pretty easily. So what changes though? So this system has a lot of benefits, but it releases CO2, which causes these issues that we've talked about the whole rest of the class. Major problems with the economy, like increasing sea level, which would require a huge amount of cost to deal with. So we want to eliminate CO2 and eliminate the burning of fossil fuels and transition to renewable energy like solar. And so let's look at some of the issues with that. So when we're transitioning to solar, the first thing to note is, of course, that you don't get solar power at night. So here's our society, here's our power demanded, here's our solar panels that we'll put in Arizona. So it makes the most sense to put our solar power where it's the sunniest, right? And so we have some amount of solar power. And in this case, I've drawn it where it doesn't quite meet demand, even when it's sunny, but it definitely is not going to meet demand at night. So we want to complement our solar power with other sources of energy like wind. And so we want to put those in the places, we want to put our solar farm where it's the sunniest, and we want to put our wind farm where it's the windiest. And so right there, that's something that cost is going to increase because of this constraint. So before we had a system where we could put our coal power plant, it didn't need to be right next to us. And we didn't want it right next to us because there was air pollution associated with that, but it could be relatively close. And so you didn't need huge transmission lines to get the power from where you're burning coal to where you need it. But when it comes to wind and sun, there are a lot of places that aren't very sunny, and there are a lot of places that aren't very windy where people still live. So you need to transmit that energy much longer distances. So you end up having to kind of remake the electricity grid so that you can transport energy a lot longer distances. So that's one thing that kind of increases the cost of energy. But so if I'm going to put our solar energy, so here's our solar energy each day of this week, and I'm going to layer on top of that our wind energy. So that's getting us an additional amount of energy on top of that. So our blue is solar plus wind power. supplied, and then we're comparing that to the power that's demanded. And we see, we still have this mismatch when we compare it to our fossil fuel situation. We had this kind of clean meet of supply and demand, where we had this demand of whatever people wanted, and then we're changing the power supply exactly to match the demand. Where if we just kind of think about renewable energy in the baseline case here, the amount of energy supplied by nature does not necessarily meet demand in time. So one thing is that we have this period of time each day when the sun is out and it's relatively windy, where we have more power supplied than demanded. And that's what they were talking about in that video, that if you have a situation where you don't have the ability to store the energy and you have more power supplied than demanded, you have nothing to do with that electricity other than you have to like turn off the solar panels or shut down the wind farms or curtail the energy, they call it. It's basically just waste that energy. But if you are able to store this energy, so pump this energy into batteries, for example, then you could move it to later times in the day when you don't have enough energy. So that's one of the major things, is you want to be able to store this for later use. So you want to have, let's say, major batteries on site. So then you can take that energy that's oversupplied in the middle of the day and use it later at night when people want to use it. So that's one component. Okay, so, but we still, in this situation, we have a situation where we don't have enough energy supplied at night. So we have what's called unmet demand, where we're storing some of the energy during the day and we're releasing it at night for a while, but then we run out. And so each night from like the hours of, let's say, 3 a.m. until the sun starts coming up at 6 a.m., we don't have enough energy. And so we end up needing to kind of weigh what's called overbuild, where we need a lot of wind farms and a lot of solar farms. Yeah, so we would build more wind farms and more solar farms so that we can meet energy demand even in the middle of the night. So you'd need like a lot of wind farms for that. Other things that can help us here that are also represented in En-ROADS would be increasing, for example, energy efficiency. So recall that in En-ROADS, we have energy efficiency levers here. So like buildings and industry. If we have our buildings and industry electrified and much more efficient, what does efficiency mean? Remember, if we look at energy demand by area, and if I go from energy efficiency of status quo to energy efficiency highly increased, what is that doing to global primary energy? It's not necessarily shifting around the sources. Like, it's not like it changes, swaps out one for the other. It's just changing the total amount of energy used. So energy efficiency, and of course we can also see this in our Kaya graphs, that's here. Energy efficiency is going to decrease the amount of total energy used. So going back to our graph here, this energy efficiency would essentially move the power demanded down. And so that could help us match supply and demand under this new energy system, right? So if we move that down, then we have less of these time periods where demand is higher than supply. There's also this thing called demand management. And so demand management would be policies or campaigns or just trying to advocate that people use their most energy intensive appliances when there's the most energy available from the sun. So it would be like, instead of doing your laundry at night, instead of washing the dishes at night, instead of using all of your appliances at night, anything that can be run in the middle of the day when we have all of this solar energy should be run in the middle of the day. And we should also be charging our electronics and things like that in the middle of the day. So we can try to manage demand and line it up better with the supply of energy. So in this case, that would be like moving these peaks towards the middle of the day. And so that would help reduce the amount of time spent where energy demanded is higher than energy supplied as well. And so overall, we also just need a system that can handle fluctuations or time periods of reduced wind and sun overall. So if we increase our, so we have our wind, we have our sun down here, we have our wind, but we're also going to need more, we need like a geographically distributed system where we also have a solar farm over here, and we also have a wind farm over here, and they all have storage. And the reason for that is that you want the solar and wind farms placed in the right place so that when it's less windy over some of our wind farms, so let's say it gets less windy here, you need it to be more windy somewhere else. So you need these to be far apart in space so that there's not like a correlation between the windiness of your wind farm here and your wind farm here. Because if there is, then you would have all of your wind disappear at the same time and you'd be in big trouble. So you need it to be such that like when it's not very windy here, it's windy here, or vice versa. And it's not very windy here, it's windy here. And so then you can maintain your total amount of wind power. And same thing with the sun, right? If it's cloudy over this solar panel, then you want it to be extra sunny over this solar panel. And then you will maintain your total amounts of solar power generated. And so that's an additional constraint, is you have to think about where to put all of these wind and solar farms so that they don't have a time period where they're experiencing low wind and low sun at the same time. And so that's actually what I'm studying, is that I'm trying to study the weather patterns and look at wind and solar variability and think about a system that would be robust to droughts in solar energy, right? So we typically think of droughts in terms of precipitation, but if you think about an energy system of the future that's mainly renewable energy, then a drought in the sun, meaning that it's cloudy, could also be a major problem for society. And same with a wind drought, that if you have a situation where it's very non-windy over a large geographical area, then that would be a major problem as well. So we want a system that can be robust to wind and solar droughts. And also thinking about that could even happen at the same time when you get like an increase in energy demand. For example, if it happens to be really hot when a wind and solar drought occurs. So if you have a wind and solar drought during a time period when the temperature related demand floods, that would be like, okay, it's very hot, and so people all turn on their air conditionings. And so that's going to mean that this demand actually goes up. That's even then a bigger problem for the system. Or it could work the other way with temperature as well. So we're trying to change all of our heating systems so that they're more like reverse air conditioners. So they're electrical rather than using methane, so natural gas. So if it was, in the winter and you had a situation where it's cloudy and not very windy and cold, that would be stressors on the energy system in 3 different dimensions, because it's not very, you have low supply of energy, low solar power, low wind power, and high demand of energy because it's cold. And so people are turning on these electricity using heat pumps. And so that would be another stressor. So this is all just to say that this new system that we're talking about, that's not a fossil fuel system, has a bunch of challenges associated with it and has a bunch of engineering obstacles that need to be overcome. And then other things to consider are that we are trying to electrify transportation, right? So if we want to eliminate CO2 from oil consumption, then we have to switch our cars from being internal combustion engine cars, from gasoline burning cars, into electric cars like Teslas. And we see that, of course, in En-ROADS as well. I go to home. So transport, electrification. So electrifying transport means that more of our energy is going to come from electricity. And so that means that all of these things that we're talking about in here become more important because we're using more electricity if we're plugging in all of our cars, and instead of burning gasoline, we're using electricity. So that makes all of this more important. And then another thing to consider is that all of this CO2 that we've already put into the atmosphere, that's changing the global climate. It's changing temperature. So it's going to increase demand for air conditioning, for example. That's like the obvious one. But it should also change winds and clouds and all that stuff as well. And so that's something that we're keeping an eye on in meteorology and climate science, is how to build an energy system that can harvest the most wind and solar power, and keeping in mind that the climate itself is changing. And so it may change where the best wind is and where the best solar power is. And it might change the frequency of wind droughts and solar droughts, et cetera. So this is the type of thing that I'm studying, is kind of the covariability between wind and sun and temperature. So I have one video here about the electric grid. So this is gonna look at a lot of these same issues that I was just talking about, of demand management and kind of how a renewable energy system requires a new way of thinking about the electricity grid.
Our current electric grid was conceived more than 100 years ago, when electricity needs were simple. Power generation was localized and built around communities. Most homes had only small energy demands, such as a few light bulbs and a radio. The grid was designed for utilities to deliver electricity to consumers' homes and then bill them once a month. This limited one-way interaction makes it difficult for the grid to respond to the ever-changing and rising energy demands of the 21st century. The smart grid introduces a two-way dialogue where electricity and information can be exchanged between the utility and its customers. It's a developing network of communications, controls, computers, automation, and new technologies and tools working together to make the grid more efficient, more reliable, more secure, and greener. The smart grid enables newer technologies to be integrated, such as wind and solar energy production and plug-in electric vehicle charging. With our participation as informed consumers, the smart grid will replace the aging infrastructure of today's grid, and utilities can better communicate with us to help manage our electricity needs. The smart home communicates with the grid and enables consumers to manage their electricity usage. By measuring a home's electricity consumption more frequently through a smart meter, utilities can provide their customer with much better information to manage their electricity bills. Inside the smart home, a home area network, or HON, connects smart appliances, thermostats, and other electric devices to an energy management system. Smart appliances and devices will adjust their run schedule to reduce electricity demand on the grid at critical times and lower consumers' energy bills. These smart devices can be controlled and scheduled over the web or even a TV. Renewable resources, such as wind and solar, are a sustainable and growing source for electric power. However, renewable power sources are variable by nature and add complexity to normal grid operations. The smart grid provides the data and automation needed to enable solar panels and wind farms to put energy onto the grid and optimize its use. To keep up with constantly changing energy demands, utilities must turn power plants on and off depending on the amount of power needed at certain times of the day. The cost to deliver power depends on the time of day it is used. Electricity is more costly to deliver at peak times because additional, often less efficient power plants must be run to meet the higher demand. The smart grid will enable utilities to manage and moderate electricity usage with the cooperation of their customers, especially during peak demand times. As a result, utilities will be able to reduce their operating costs. By deferring electricity usage away from peak hours and having appliances and devices run at other times, electricity production is more evenly distributed throughout the day. The power being used right now was generated less than a second ago many miles away. At each instance, the amount of electricity generated must equal the consumption across the entire grid. Smart grid technologies provide detailed information that enables grid operators to see and manage electricity consumption in real time. This greater insight and control reduces outages and lowers the need for peak power. In control rooms across the grid, engineers will be able to more precisely and predictably manage electricity production, reducing the need to fire up costly secondary power plants. The distribution system routes power from the utility to residential and commercial customers through power lines, switches, and transformers. Utilities typically rely on complex power distribution schemes and manual switching to keep power flowing to their customers. Any break in this system caused by storms, bad weather, or sudden changes in electricity demand can lead to outages. The smart grid's distribution intelligence counters these energy fluctuations and outages by automatically identifying problems, then rerouting and restoring power delivery. Utilities can further use distribution intelligence to predict and manage electricity usage with the cooperation of their customers, leading to lower production costs. The charging of a plug-in electric vehicle can be managed over a home area network, or HON. The HON can balance the demand for electricity across the household and prioritize between the electric vehicle and other appliances to manage electricity usage and reduce costs. With smart grid technologies and consumer participation, utilities can more easily handle the increased demand for power to run the electric vehicles and ensure charging needs are met. By adding more plug-in electric vehicles to the grid, we have the potential to reduce fuel costs, lower our dependency on foreign oil, and help reduce greenhouse gas emissions.
Okay, so this is hopefully the future, that we have this smart grid that has a bunch of wind and solar integrated into it. And there's kind of this demand management side of things. There's this increased energy efficiency side of things. Hopefully we'll have apps on our phone very soon that will allow us to see in real time what the cost of energy is, and so then can incentivize people to move the consumption of electricity towards the times of day when they are least cost. And the United States has very good resources for wind and solar energy, so it seems like a system like this is relatively feasible in the United States. So here's just some maps of where it's sunniest in the US. So it's sunniest in California and in the southwest, the desert southwest. And then it's windiest. We have some of the best wind resource in the world in the central kind of lee side of the Rocky Mountains in the central United States. So we have good wind and solar resources. They've studied, how much of the land we'd have to use in the United States to get to 100% renewable energy in the United States. And that's what these dots are showing. So this is the amount of land covered by wind farms. So it's a lot. So it's like the size of a state. So this is sitting over Iowa. And that doesn't include, so like a wind farm, there's a bunch of space in between the wind turbines. So it's not like that land is completely used up by wind farms. You can kind of put them on land that's already agriculture, already farms, for example. but you know, when you think about like, okay, this seems like a lot, but it's actually not that much considering how much we already use for other things. So this is a map of the United States where it shows how much land is used for various end uses. So, for example, the biggest thing that we use land for in the United States is cow pasture and cow ranges. And then we also have like livestock feed and the food that we eat. So these three combined are like, and then we also have these other animals. So these three boxes combined make up almost half the country or more than half the country. And that's just agriculture. And we can kind of put wind farms on top of those things. So it's a lot of land, but it's doable, it's feasible. And with this demand management and with a smarter grid, it seems like a system that's, you know, something that we can actually get done. But it does come at costs. It comes at the cost of having to build the new system. It comes at the cost of having to store energy, which is still very expensive. And so those are the main things that we really are rooting for to come down in costs in order to make this transition and to eliminate that term in the Kaya identity. That's the amount of CO2 emitted per unit of energy, which is really what needs to get to zero to stabilize global temperatures.